All right, these are the notes after the pendulum activity, where you gave little tiny taps to the pendulum the right time, and you saw that even though each individual tap didn't really do much, after a while, all those little taps added up, and the pendulum was doing really, really big swings, even though you never had to push it with one really big swing, you just did a bunch of little swings. So hopefully you saw that. So the big ideas from this, and this goes in your packet. There's a section for notes under that, on the bottom half of that page. Putting little bits of energy in over time can result in a lot of energy out. That's one of the big ideas here, is we're just doing little tiny taps, and after a while we get really big amplitudes. Now we're not really getting more energy out than we put in, it's just kind of like that energy's adding up. Another thing that you should have learned from this, another big idea, is that if you don't do the taps at the right frequency, at the natural frequency of the pendulum, or if there's a lot of energy loss, like a lot of friction, you're really not going to get these big amplitudes. You're not going to get a lot of energy out. So initially you should have tried it with just every second tapping the pendulum and nothing really happening at all. But if you hit the natural frequency of the pendulum, then you end up getting these really big amplitudes. So there's some vocabulary here, so you can go back in your packet to the vocab sheets and find this vocab and check it off and make any extra notes as you need to. So natural frequency, the frequency at which an object will vibrate when struck. The damping, the fraction of mechanical energy lost from an oscillating system in each oscillation. So all you have to understand with this is, with a pendulum, as it swings back and forth, it's slowly going to die out, and that's due to damping. That's the mechanical energy that's lost every time it swings back and forth. If it loses a lot of energy every swing, we'd say there's a lot of damping. If it doesn't lose a lot of energy, then we'd say there's not much damping. The driving frequency, the frequency at which we are forcing something to oscillate. This is called a forced oscillation. So the first part of the activity, when you tap the pendulum string once a second, that was your driving frequency. That was not matched up with the pendulum's natural frequency, so we didn't get it to resonate. We didn't get these big amplitudes. So resonance, this is sort of the main idea of everything. So this occurs when the driving frequency is the natural frequency. So when you tap the pendulum, you put in those little amplitudes at the same frequency as the pendulum would vibrate on its own, that the pendulum would swing back and forth on its own, we say the pendulum resonates. The main idea here is many little amplitudes, all those little taps, add up to huge amplitudes. You can also resonate something when it's not exactly at the natural frequency, it just won't resonate as well. But we're just going to focus on when we hit the natural frequency perfectly, all these little taps, these little amplitudes add up to really, really big amplitudes. All right, so back in the middle of your packet here, so we're past the vocabulary now, looking at standing waves. So the idea here is, what if we send a bunch of pulses down a spring and let them reflect back? So we have a spring held between two people. You'll see a video of this in a second. Actually, first you're going to try this, and then you'll see a video of this. But a spring held between two people, like the snaky spring here that we had in class, so the big one, not the slinky, the snaky. And we're going to send, one person is going to send some pulses down the spring, and they're going to reflect back the other way. What's going to happen with those? How will they interfere with one another? So you know some basics. If a pulse is on top and another pulse is on bottom, because they positive amplitude, negative amplitude, they're going to destructively interfere. And if one pulse is on top and one pulse is on top, they're going to constructively interfere. They're going to get bigger. And what's this going to look like? So the task here that you're charged with is, can you get the spring to resonate? Remember, resonance is when you're vibrating something at the natural frequency, and if you send little waves down, it's a bunch of little waves down, can you get big waves out of that? Also, resonance isn't just at the natural frequency. There's other frequencies that it can resonate. Natural frequency is like the lowest one. That's what we think of. So can you get it to resonate at different frequencies? So what I want you to do is, you're going to go try this right now. You may need to move some tables in the classroom. These are the snaky springs that you're going to use. They should be set out for you. And you can stretch them out to be about half the classroom should be fine. You can get a good amount of tension under this, but what you want to do is put your finger inside here and hold it this way, and don't stretch it so much that it hurts, then it's too much. Don't hold it like this, because then what's going to happen right here is this part will get overstretched, and then the slinky will have the snaky will have a permanent kink in it. So you're going to try this. You're going to each team will get a snaky, and you're going to spread out again about half the length of the classroom, and one person is going to send a bunch of waves down, and you're going to try to get it to resonate. So you're going to do little amplitudes and see if you can get big amplitudes out. If it's not working, try a different frequency. Try a different frequency. When you get it to resonate, it should be really obvious. You should get amplitudes this big, you know, the waves going up and down, something like this. So it should be really clear. So I want you to pause the video, and I want you to go try this now with your team. Go. All right, so if I send some pulses down the spring, so I send a pulse, I send a pulse, we see they interfere with one another, but there's nothing terribly interesting happening. If I time the pulses correctly, I can get them to interfere with one another in a special way. And so here, when you want to see, if you look at my hand is only going up and down this much, but the wave has a much bigger amplitude on that. So we can see that the spring is resonating here. All these little pulses are adding up to bigger ones. So one of the other questions we asked was, can we get this to resonate at a different frequency? And we can. So again, it's just getting the right timing. I'll show you not resonating. So if I hit here, maybe I'm just going to get one automatically, but sometimes it's hard. It's easy to get the natural frequency because your hand sort of goes for it. Yeah. And hopefully you saw it when you did this. But let's see. Let's get the next one up here. Here we go. Yep. And when we really get it spot on, you can see how much bigger these amplitudes get compared to the little pulses I'm sending down here. And let's see. The other thing we can look at is what's the longest wavelength we can put on here. That would be the lowest frequency, and it's a little more boring, but there we go. And this is actually, we see 1/2 of a wavelength is visible here. So the wavelength of this is twice the distance between myself and Mr. Bosniak. And that's how you can make some standing waves on a spring. Next, we're going to look at how these waves are formed. All right, what you should have seen in the classroom, and then what you just saw in the demo that Mr. Bosniak and I did, was a standing wave. This is a wave that remains in a constant position. We're going to take a look at how a standing wave is formed right now. So we have the incident pulses. So the incident pulses are coming down here, going to the right, and I've paused it here. I'm going to resume it in a second, and the reflection is going to be a fixed end. So with your team, I want you to decide, what is this pulse going to do when it hits this fixed end? Is it going to stay on the same side, or is it going to flip? So talk about that with your team. And let's see if you were right. And it flips over. So what we're seeing here, the red is the incident pulses, the pulses coming to the right. The blue are the reflected pulses. And the black is the superposition. It's what we would actually see. It's what we actually see on the snaky spring. So this is what we see here. Notice a few things. When the red and blue perfectly line up, we have a much bigger amplitude for the superposition. Again, it's resonating as the smaller amplitudes are combining to make bigger amplitudes. And we also notice that, for instance, this spot here that's labeled with an N, the superposition has no displacement. We don't have the wave going up or down or anything. It's just sitting there. And the reason that is because those two waves, the incident wave, the red wave moving to the right, and the reflected wave, the blue wave moving to the left, are always perfectly canceling each other out. Whatever, if one's positive 2, the other one's negative 2 for the amplitude. And they're always perfectly canceling each other out. So this is a spot of no displacement. Here's a spot of no displacement, no displacement. And these nodes, we call them nodes, N-O-D-E, no displacement, are not moving left and right. And that's one property of a standing wave. Also, we have these spots that are the complete opposites of nodes, where we have maximum displacement. Now, not all the time. Sometimes we'll see if we pause it, oh, I just missed it. But we can, if we pause it here, so this is where it's at maximum. So this is what we call an antinode. This location, this left and right location right here is an antinode because it's a spot of maximum displacement. And even though sometimes we can do, whoops, I'm not sure what happened there. We could pause it where there's almost nothing on the string itself. This is still the antinode location. The antinode we don't say is up here, it's this sort of the position on the x-axis where that is. So there's the basics on how a standing wave is formed. I'm going to start it over again, and I'm going to do from a free end over here. So while this is queuing up, I want you to discuss with your group, will we still get a standing wave? Will it look any different? What's going to happen when the incident wave hits the free end? So discuss those things here, and I'll pause it. And you can pause the video, and I want you to discuss what do you think is going to happen? Can you still get a standing wave from a free end? All right, so discuss with your team. Go. And hopefully you've paused it, you've discussed it, and now you've played the video again. And here we go. Let's see what happens. So we have the incident pulse in red, in the blue, and it does not flip because there's no fixed end, nothing to pull it down. And looks like we still have some nodes here, some spots of no displacement that are not moving left or right. So we still have a standing wave. We still have resonance because we have these little amplitudes making much, much, much bigger amplitudes. Now, it's a little different here because this end here, we call it a boundary condition. We'll study this a lot more. But the boundary, the end of the standing wave, before was a node. It was a fixed end. It couldn't vibrate at all. And now it's an antinode. It's a free end and it can vibrate. So we notice, and this will be a trend, we'll see this a lot, that when we have a free end here, the standing wave is an antinode. And when we have a fixed end, the standing wave is a node. All right. So let's get back to the notes here. So how is a standing wave formed? So this is the part of the notes. This is formation of a standing wave. So these are the steps. You send a wave down and they're reflected. So send waves down. They bounce back. Either a fixed end from a free end, doesn't matter. You can get a standing wave with both. The reflections interfere with more incoming pulses. So you have reflections coming back, incoming pulses coming in, and those are going to interfere. At points of max constructive interference and points of always destructive interference don't move. So the max constructive interference, that's the antinodes, where it's going all the way up and all the way down, and always destructive interference, those are the nodes. If those don't move left and right, then we say, oh, it's a standing wave. It's not going anywhere. So take a minute to write these down in your notes. You can pause the video if you need to. And hopefully you have it all written down now. So I want you to think about a standing wave. The main idea for a standing wave, it's just the amplification of incident waves. So incident waves are coming in, and they're interfering, they're reflecting, interfering with more, and they're just getting bigger. That's the main idea here. There's nothing special beyond that. We'll talk a little bit about when a standing wave can't form. But the idea is you have the standing wave, the incident waves, they line up perfectly with the reflected waves, so we get these points of maximum displacement or no displacement that don't move left and right. All right, how to draw a wave. You want to put a dot where your wave starts. You're going to put dots at all the points where the amplitude is 0. It's like we did, I think, at the very beginning of the packet where we were doing position versus time, velocity versus time, acceleration versus time, energies, where we place dots initially. That's a good strategy with this. So you put points where the amplitude is always 0 at the nodes. Put dots at all the points where the amplitude is at its max. Those are the antinodes. So I'm going to, this is the wave that you're going to draw. I'm going to start it up here. You could certainly start it at a node as well. But these are the dots I'm going to put in. So it's a dot here at an antinode, and then 2 dashes over, and then we have a node, 2 dashes over the antinode, 2 dashes over the node. And again, the antinode is technically here, but the wave will be up here, so that's where we're putting the dot. And then we're just going to connect everything. To show a standing wave, we do a solid line, and then for half a period later, we do a dashed line to show that it's staying in one spot. That's how you need to indicate a standing wave. So this is how you can do it. So solid line, just connect the dots. And this is kind of like a cosine wave. And then we do dashed lines, which would be a negative cosine. And these dots allow you to get nice curves with these waves. All right, so parts of the wave. So label away. We have the nodes and we have the antinodes. Nodes are locations of no displacement. Antinodes are maximum displacement. Other parts of the wave, we have the crests, and all these words are in your vocab sheets at the beginning of the packet. Crests, and we have the troughs at the bottom here. So crests and troughs, just high parts and low parts. Another way to say positive amplitude, negative amplitude. I mean, all of these have, all this is positive amplitude, but max positive amplitude or max negative amplitude are the crests and the troughs. So we have parameters here, some measurements we make on a wave. So we have the wavelength. The wavelength is from the crest to the next crest. Biggest mistake, most common mistake people make is they go from crest to here. But remember, the solid line is 1 instant in time, and the dashed line is half a period later. So we could also go from trough to trough. We could go from a wavelength from here to here. We could also do wavelengths, and this is a little bit trickier, so here it's starting to go under, so we could go from where it's going under to where it's going under again. This would be one whole wavelength. Basically, you start at one point on the wave, and then you end the wavelength when the wave starts repeating itself again. Amplitude is the distance from equilibrium to the maximum displacement. Most common mistake people make is they go from maximum displacement to maximum displacement over here and say that's the amplitude. That's really twice the amplitude. So there's another amplitude there that you can measure. Just a heads up. Sometimes this is a confusing point for students. In your math class, I believe you say this x-axis is time, and sometimes we say this x-axis is time, and sometimes we say it's position. If we change the x-axis to time, then we're just looking at sort of one spot and a wave sort of traveling, past our little viewfinder here as it goes up and down. And we're just looking at one spot, so the time would actually be, they give you different wave parameters. So from here to here, that would be the time it takes to complete one cycle, so that would be the period. Just make sure you check your axes on this. But be careful, we talk about it differently in math and in physics, so check that axis. All right, that's the end of the notes.